the speaker. We will continue with Patrick Pilarski. Are you there? Great.
Yes, I am. I'm just getting all the tech set up here. Hopefully you can see my hand. And can you hear me?
Yeah.
Good. And can you see my screen in presentation mode?
Yeah, I can see the slide.
Okay, good. And you can see me again, I hope. I can see me. I have a monitor iPad just in case, so I can actually see hopefully what everyone else sees. But is it okay to take it away?
Okay, so introducing the next invited speaker. Dr. Patrick Pilarski is an associate professor in the Division of Physical Medicine Rehabilitation, Department of Medicine at the University of Alberta. And he also co-founded DeepMind's Alberta office, where he's a senior staff research scientist. He's a fellow and vice board chair of the Alberta Machine Intelligence Institute, and is a principal investigator with the Reinforcement Learning and Artificial Intelligence Laboratory at the University of Alberta. So please welcome to Dr. Patrick Pilarski.
Thank you very much, and thank you very much to the organizers. I really appreciate the chance to speak at this workshop. I've enjoyed the amount of it that I was able to co-locate with our time zone, and I do want to give a shout out to Matt Taylor as our 7 a.m. hero for taking the early morning spot. But still in my bathrobe drinking tea while Matt was presenting, so I just want to shout out to Matt for being the early morning hero. I had some time to at least wake up and get some caffeine. As noted, I am a professor here at the University of Alberta, or I guess for the last 16 months, a professor in my basement. But I am going to be sharing primarily today work that we've done over the last 10 years at the University of Alberta, considering tightly coupled human-machine interfaces. And so by this, I mean a very close or intimate partnership between a person and machine that are learning about their world through trial and error process of reinforcement learning. And in particular, I'm going to share with you a view that constructivism is really important in these tightly coupled interfaces. And that is in fact something that enables those partnerships to very closely align and to allow the machine to align to the human in keeping with the theme of the workshop. So my goals for the talk are to be able to advance my slides. My goals for the talk are really threefold. One, I'm going to define for you constructivism and the phrase tightly coupled in the context of human-machine interfaces, in particular neuroprostheses. I think this is a nice complement to a lot of the work that we've already seen presented, because it does represent this very uncommon coupling between a human and a learning machine. I'm going to propose something that might be controversial, maybe not, that for maximum potential, tightly coupled interfaces should be partially or fully constructivist. Again, I'll define this for you in a bit. And then give some concrete examples from our lab here at the university and our partnerships on how we've worked to construct predictions, policies, representations, and state, and even models in upper limb prosthetic interfaces. So hopefully everyone's okay with that. I'm still looking at people's faces. All I see is Miguel. Hopefully that sounds like an okay roadmap for today. So I'm going to start with some motivating examples. I'm going to try to paint pictures for you of what I mean by tightly coupled before actually precisely defining it. And so one example here is I'm taking from the Neuralink initiative, which is direct cortical implants. Neurotechnology, which is implanted directly into the surface of the central nervous system, and in particular, the human brain or an animal brain. So in these cases, we can see electrodes directly implanted into the tissue of the mind or the brain. We, in fact, are starting to see a revolution in neurotechnology that directly connects to the brain. It used to be that we were limited to less than 100 or sometimes less than a dozen interfaces or electrodes that were implanted within the surface of the neural tissue. And now we're seeing the potential to, in real time and through wireless technology, record thousands and thousands of signals, and in fact, potentially put signals back into the same tissue that's being recorded from. So this is a revolution. It's not just Neuralink. There's many other companies that are looking at incredibly high density neural interfaces. And yes, just in case anyone's wondering, this is actually, the Neuralink example is actually a sewing machine that threads little interfaces directly into brain tissue, whatever you feel about that. It's not just for the brain, other parts of the central nervous system. This is a partnership between Brown and Intel AI and others that is looking at how you might in fact start to link in a very direct way via electrodes to the spinal cord, so as to potentially bridge or to mediate damage to a spinal cord or spinal cord injury. So looking at ways to create tightly coupled interfaces that will connect parts of neural tissue to other parts of a body's neural tissue. There's another example, which I think is closer to the work that we're doing at the University of Alberta, and I think is really exciting. This is work from Max Ortiz-Catalan and his team on muscle, bone, and nerve integration. So we've actually seen a revolution in neuroprosthetic technology for the extremities, and that we now see we can actually implant robotic devices directly into the bone structure of the human body. So provide mounting points for robots such they can be directly affixed to the human body in a mechanical, physical way. And at the same time that those mechanical interfaces, you can see this in the X-ray diagram on the slide here that's taken from Max's paper, you can see that those physical interfaces provide electrical interfaces to muscle tissue and neural tissue, bidirectional interfaces directly into the body. So again, I'll just say very briefly, you could clip a robotic limb directly onto the body. It attaches to the bones and attaches to the muscles and nervous system at the same time. This is the kind of flavor I hope you take from the tight coupling I hope to speak about in this talk. It's not just, those are research examples I showed you on the previous slides. We also see that there are examples of tight coupling between humans and machines, learning machines, that are actually in full clinical use, that are being prescribed to patients and worn on a daily basis. Commercial prostheses, this is near and dear to the heart of us working here at the university on upper limb robotic prostheses. You can see that these devices are actually being used in public life. And in fact, there are now devices that you might construe as being tightly coupled, devices that read biosignals from the human body and in some cases actually deliver feedback back to the human body in a very much persistent real-time way, are available for very low cost at a number of consumer electronic stores. So you could actually go out and buy what might be construed as a tightly coupled interface. These are all my way of bridging into this slide here that I'm showing now, which is that we can imagine two agents, in this case, a human agent and a machine agent, and that machine agent and the human agent have a diverse, complex sensory motor stream flowing to and from them. They each provide to the world around them a very detailed and in some cases disparate set of sensory motor values, and they take those same kind of diverse signals into themselves. The argument for the talk here and what I really want to place is that, in fact, machine intelligence is a core glue that holds together these two disparate streams. And in fact, that machine intelligence should be constructed from the nature or the data or the experience in those sensory motor streams. So this is my first sort of bullet point slide for you today, which is really that I think progress, especially in tightly coupled neuroprosthetic interfaces, humans and machines that are coupled in a way that allows them to live their life together in the flow of time. The progress here relies on the construction of things like the representations that they use, especially in the part of the machine, but I'm actually speaking about both the human and the machine, about the predictions that they make, the policies that they form, and the models that they generate in these tightly coupled interfaces. So now I'll get into some definitions. I'm going to walk you through a little bit of the history and literature. I'm sure many of you are familiar with Piaget, but in terms of constructivism, Jean Piaget really put forward that intelligence is actually something, and knowledge is something that arises out of the raw perception habits and the words here, elementary sensory motor mechanisms. So the idea that all that a system knows, or most of what a system knows, I will say all for now, stems from that system's experience with its own sensory motor data stream. This is the idea here, and just to make sure that we're on the same page in terms of how I'm using intelligence, here I'm going to draw McCarthy's definition of intelligence as the computational part of the ability to achieve goals in the world. And so then when we start to speak about artificial intelligence and the machine intelligence that I'm going to reference in the talk, I'd like to use again McCarthy's definition as the science and engineering of, and I'm going to paraphrase here, making machines that are able to achieve the computational part of their ability to achieve goals in the world. Maybe the intelligence is that the science and engineering of making intelligent machines, especially intelligent computer programs. So this brings me to a little bit more of the historical backdrop for this, which is really on closing loops. And I'd be remiss in not bringing up Norbert Wiener. Norbert Wiener's work on cybernetics was quite influential. And one part I want to call out for today's discussion on tight coupling is that it really focused on communication and closed loop signal passing as a way to allow systems to align in an autonomous way. Disparate parts of a system or different systems that could align through closed loop signal passing. Moving on to someone whose work I base a lot of my own work on, W. Ross Ashby, that Ashby really said that two systems with a communication channel open between them are able to start to amplify, augment, or extend each other's abilities. This is one of the positives of some of Ashby's work. And when we start to move towards tight coupling, I think it's really important. Is perhaps one of the final examples here. I reference J.C.R. Licklider, who wrote a really influential paper called Man-Computer Symbiosis, and had a body of very, I think, quite influential work as well, that spoke about tight coupling. That, and this is a direct quote, and I like to read this one out. The hope is that in not too many years, human brains and computing machines will be coupled together very tightly, and that partnership will think as no human brain has ever thought and process data in a way not approached by information handling machines we know of today. That the alignment between these two systems would in fact do something very transformative. And so I'm going to draw on this idea of tight coupling. In particular, now I do want to give you something that I consider to be relatively crisp in terms of tight coupling. And so back in 2012, and actually this was, I think, the workshop where I first met Brad Knox. This was the Fall Symposium, and there's a wonderful workshop on robots and humans interacting. And Rich and I had this paper there that talked about a continuum of interaction between a director and assistant, or a human and a machine, that was judged in terms of the bandwidth of that interaction, the latency of the interactions, and also the explicitness of the signals or concepts being passed. And so I'd like to say that the tight coupling, or the way I'd like to define tight coupling for you today in more of a clear way, is in fact the regime wherein there is very low latency and potentially very high density of communication between a person and a machine, or an agent and an agent, but that we might not have to think too much about the explicitness or the detail or the level of complexity of the things being passed. It could be bits, it could be action potentials on a neuron, it could be small signals that are transferring. So then the next piece of this talk is really saying that a constructivist perspective to these tightly coupled interfaces is in fact the right way to go to support things like adaptation, or having individual agents begin to sculpt to other individual agents, or align to other individual agents, human or machine. And in particular for the human machine case, that constructivism as applied in a tightly coupled interface is a way to allow a machine to align to the unique flow of needs and goals and objectives in a human's daily life. So my main considerations or starting points here that I'm going to root this discussion in are first the inevitable discussion about training and testing or continual learning. I'm going to say that really this perspective I'm putting forward today is one of continual learning, where a machine system, I'm speaking just for the machine, but I do mean both the human and the machine, is continually learning and not divided into regimes of training and testing. Also, whether a system is building on the first is pre-trained or tabula rasa. I would say tabula rasa, but I actually edited my slides before the talk in response to Matt's talk and his notes on the thoughts of Corey Matthews and others, is that it's very hard for us to remove all prior biases because we are still designing the code or the architectures. I buy Corey's argument that all machine learning is interactive machine learning. So I'll just say here, minimize prior biases. And that if we think about the interaction in tight coupling as a relationship or some predetermined coding channel, I think really we should view it as an evolving relationship. I'll talk a little bit about the work we've done before closing, the work we've done here at the University of Alberta. A lot of our work has been focused on individuals with upper limb amputations. Here's one of our awesome participants who's working with us on understanding how a learning machine might interact with him and how his signals might be used to control that learning machine. We've studied a variety of different settings, both with people with amputations and those without amputations, controlling a wide range of robots, everything from very simple robots right through to very complex, high-dimensional, high degree of control robotic systems like the one here that Gautam Vasan is shaking hands with. Over the years that we've worked, we've gone through a number of different case examples of how a person and machine might co-adapt and how the machine might build directly from the raw experience with the person. One of the first works that we really put forward was actually in using human delivered reward. So a human actually providing good, bad feedback to a prosthesis control system, and looking at how the person might be able to use that reward to actually sculpt individualized policies on the part of a two-joint robotic limb. Person delivering biofeedback signals to a robot, and then actually using their own reward delivered in real time to adapt the policies that system has in response to their signals. We moved on to things like learning joint synergies, and not based on some objective task measure, but on what a person actually does and how they do it. So systems that through processes of temporal difference learning build up a predictive set of the different ways the system might configure, and then use that to optimize or help coordinate a very complex control task for a person. We've also looked at this in reverse. So instead of just looking at how a person's control might be constructed through our experience, we also looked at how a system might begin to provide vibrotactile feedback or auditory feedback to a person in response to the evolving relationship they have with their environment. We looked at learning from demonstration with multiple limbs, and also looked at more what I would consider more advanced model learning, whereby we actually see systems by watching a stream of experience, or a stream of experience between a robot and its world, or a person and the robot. The system is able to build up a model of how the world will unfold. Things like looking at massive collections of generalized value functions to predict surprise or differences in the world, or using Alex Carney's methods for tidbit. This is essentially step size adaptation and temporal difference case, looking at identifying salient patterns in a world directly from the robot's experience without us actually trying to identify the different classes or cases of experience that we might imagine. The reason I bring all of these up, I should also note Ashley Dalrymple's work with her colleagues on Pavlovian control in spinal cord injuries for standing and walking and locomotion, which also builds up standing and walking policies from raw experience. And say that all of these examples are ways that a robotic system has learned to align and interact with the person that's constructed based on the raw sensory motor interactions between an individual and the system and the world around them, and not on some objectively defined task that is provided to both of them in a crisp or concrete way. Rich and I and many of our students tried to formalize this a little bit and think about those evolving director relationships in a poorly titled paper that made sure no one found it, called Communicative Capital for Prosthetic Agents. But this is a paper I think is really nice because it does talk about how a system of a human and machine system, or a director and assistant system, might co-adapt to maximize their potential realized capacity as a function of their agency. And so in service of that, I'll take one example that we unpacked in that paper, but also one of, I think, the key examples from our laboratory over the years. And that is a technology we termed adaptive or autonomous switching. This was captured in the really excellent master's thesis of Ann Edwards, and over a series of a sequence of papers. But the idea here, and it builds on conventional or classical prosthetic limbs is deployed in a medical setting, is that we often see a person who has a very limited control channel faced with controlling many different degrees of control or freedom within the system that they're interacting. So in the case of a robotic limb, a person with an amputation might only have a limited number of control channels in their residual limb by which to control their system, but that system might have a shoulder actuator, an elbow actuator, wrist rotation and flexion, hand open, close, or even multiple grasping patterns. And so what's conventionally done in many clinical systems is that a person also is provided with a switching channel, either a physical button that they could hit with their chin, or a co-contraction of their muscles by which they could switch their control between the different modes or functions of this system. And so what I think was really a great example about adaptive switching is that in this, the system, the robot limb, was building up predictions about what a person would use, rank ordering those predictions, and then using those real-time online learned predictions to rank order and change the control interface for the person. And we showed that by learning what a person wants and when they want it, the system was able to reduce the speed by with which someone was required to do a task, and also the number of manual interactions they required to complete a series of different reaching and grasping tasks. This was really cool. And also we studied the way that that those predictions were fed back to the person in a vibrotactile way, so that the person better understood the intent of the robotic system, or the future outcomes of the choices being made by their robotic partner, to really increase the capacity of that tightly coupled partnership. So I'm going to close. I think I have 2 slides left here. And I wanted to say that from those examples and from our experience over the last decade, is that in this setting where we have 2 different agents, a human agent, especially, and a machine agent, and the sensory motor interface between them is very tightly coupled and also very diverse and dense, is that we found that constructing that glue, constructing the interface between them, and constructing their relationship based on their own sensory motor experience has been very fruitful, and allowed systems to do what people want, when they want it and how they want it, without us trying to enforce some kind of task structure upon a person who is also a constructivist entity building their world around them. So in summary, really, I'm making the argument here, and I hope that you'll at least consider it, even if you don't buy my story at present, that constructing representations, predictions, policies, and models from ongoing experience lets tightly coupled interfaces align and specialize to individuals. And that in terms of human alignment with a reinforcement learning system, that by taking a constructivist perspective, especially in this tightly coupled setting, we can actually achieve kinds of alignment or forms of fruitful alignment that we might not otherwise. So with that, I want to thank you all very much. Hopefully we have a few minutes for questions. I know we're running a bit over time. If you want the slides, I just figured out how to put them on my website this morning, although I think there might be a small glitch in one of them. And if you do want that bird's eye overview of a lot of the ways that we've looked at constructing the relationship between people and upper limb prostheses, I encourage you to go check out the paper by Rich and I and our students on communicative capital. And I promise we'll also put an updated version into the world soon. But for now, that old version should do. So with that, thank you very much. And I hope we have time for questions.
Great, thank you very much. Is there any question from the audience? You can put the questions on the chat. I have one. Let me just there is an echo, so I will mute you, and then I will ask you to unmute again. Okay, great, thank you. So how do you think we can on any way ensure that the movements become more natural or human-like and not just more efficient? Could maybe learning from human demonstrations help for that?
Great, cool. I'm sorry there's some audio echo in the room today. So I think we found that actually one answer is that yes. One of the cool experiments I really enjoyed from our past work, and this was work by Gautam Vasan as part of his master's thesis, was looking at in the prosthetic limb setting, be able to have a person train their machine prosthesis using their biological limb. So essentially, instead of saying these are the tasks or the like optimize reaching for a cup, it was an approach to allowing someone to enable prosthesis control that affected the motions the way they wanted them to be affected. I'm going to zoom out a little bit in answering this question as well and say that I think that part of this, like there is this drive towards efficiency. If we provide an extrinsic task measure or some external measure for the partnership, then it's very likely that the machine part of the partnership will be working at all costs to optimize the trajectory towards a cup or the way a gesture is performed. According to that external measure, if we start to separate out the observation and action spaces, the perceptual spaces of the two parties, and we also start to force them, in fact, to begin to model the reward functions that they're each following, I think we can start to see much more natural or much more, for the prosthesis case, much more human movements, but we'll also see a much more flexible interaction or relationship that builds in that partnership that better addresses the needs of the individual working with the technology. So that's my view on that particular situation.
Okay, great. Thank you very much. So we have time for one more question. You can hurry before I take it by myself.
Hi, Patrick. I was just wondering, I mean, there's this whole view about Neuralink and all these things where they say that it sort of increases the rich-poor divide in the sense that the rich will be able to afford such technologies and become more capable while, sort of leaving the poor behind. Just wondering what your views on that are. I know it's not a technical question, but I was just wondering what you think of this.
I think that we're seeing alternatives to some of, like, as we start to see the increase in computational ability for the systems that are part of our daily life. Like I'll use one example. One of the armbands I showed you earlier in the talk is a myoelectric recording armband. It measures the electrical activity at the surface of muscle tissue and sends that wirelessly to a computer. It's very inexpensive. You could get it for like 200 Canadian dollars or 250 Canadian dollars, and it talks to any personal computer device. It used to be that technology cost us as researchers somewhere around the order of $60,000 to get a system. But by a process of scale in sensors and actuators and computing technology, we're now seeing devices like that are becoming very expensive. We see that prostheses that sometimes cost like these are systems that might cost upwards of hundreds of thousands of dollars, are in fact now being 3D printed in a do-it-yourself way and are still being able to fulfill the needs of people with amputations. So I actually think that although there's the potential for us to see some of these technologies remaining at a very high cost point, that there are lots of forces, very positive forces, I hope, and lots of initiatives around the world on creating open source, inexpensive, accessible alternatives that are just as good as the others. And so I have a lot of optimism and hope here that we'll be able to make this technology accessible and openly available to everyone. We then have a lot of considerations as a society about how we all come together to agree on how to best ethically and socially use those technologies. But I do think the access to them is something that I'm optimistic will not be gated by substantial paywalls, explicit or explicit.
Thanks, Patrick.
Great. So thank you once again, Dr. Patrick Pilarski, for your participation and interesting presentation.